again, I'm sure it's working. I'm assuming it's working with, yeah, cool, okay. Yeah, so the chat will be recorded as well. So, I mean, like, I can technically close the chat, but I mean, I'm assuming a few people probably want their questions answered as well. So I'm going to keep the chat open even though it's going to go into the recording. Yeah, hopefully that's not an issue. I will turn this on because my laptop is slowing down considerably. Alright, cool. Okay, okay, we got functional groups wise. So we got reactivity. So we just talked about reactivity increasing from alkanes to alkynes due to bond strength, and then alcohols going to primary, secondary, tertiary. We've already known. A few people already, I guess, talked about that in the chat as well. But in terms of alkenes, but pretty straightforward. You need to know all of them. So primary, secondary, and tertiary. We should probably know how they work, right? Primary is like all of these depend on the number of I guess hydrogens technically connected to the one with the OH group in it. And then aldehydes, pretty straightforward. Also, don't mind the syllabus points below. There were like a ton of syllabus points, so I didn't bother to, I guess, like copy each syllabus point in because there was literally a ton on the QCAA syllabus. So yeah, don't mind that. Alright, more about functional groups. So we got ketones. That's just basically a double bonded oxygen, right? So it's basically same as aldehydes, but aldehyde is on the terminal carbon. So very important, obviously, to know that it's on the terminal carbon. Whereas in the ketones, it is just anywhere but the terminal carbon. So it's just within the chain, right? And then I guess carboxylic acids. We should notice as well. That one is essentially where we have C, right? OOH, right? So COOH essentially, right? So you technically have a carbonyl group, which is the double bonded oxygen, plus an alcohol connected to it, right? And then you've got esters. This is basically where you have boom, boom, and then you've got another side connected to it as well. So we will talk about esterification a bit more in depth, but generally you need to know these suffixes. So O8 for this. So ethanoate or something, butyl ethanoate, which means it's a butyl connected to an ethane, what was an ethane, right? So methyl ethanoate is an example there as well. And then you obviously need to know haloalkanes as well, which is pretty straightforward. It's just a halide group. So remember fluorine, chlorine, chlorine, bromine, iodine, and then there's technically like even more than that if you go down as well. So, and then the prefix fluoro, chloro, bromo, iota. Alright, so I'm like fast tracking these because I'm sure these are not too bad. And then you've got more functional groups, right? Amines or amines. You can also have primary, secondary, tertiary. Same with the amines. You can also have primary, secondary, tertiary as well. Functional group is just basically an NH, as you can see there. It's just a nitrogen group connected to it. Amide. This is basically a double bonded oxygen connected to it. So if you have C, double bonded oxygen, NH2, right? Similar to that. So this one is also a bit higher yield. I wouldn't say like it's not like important at all. Nitrile is a bit like not as important, I would say. So yeah, that one is like essentially a triple bonded nitrogen, right? So that's important too. All right, awesome. We're getting through these quickly. All right, so this is the most important part of, I guess, nomenclature and naming compounds overall. So the priority table, right? So essentially, when you have what we call polyfunctional compounds, so multiple like functional groups together, right? When you name it, you need to name it based on the suffix and the prefix, right? But then where do you put the suffix? Do you use the suffix or the prefix on which kind of functional groups? So we determine that based on this table. So carboxylic acid is essentially the highest one, alkane is the lowest. And you can imagine alkane is the lowest because, it's, not as important because basically almost anything has like one bond, right? So that's not as useful. But carboxylic acid will always get the suffix. So whatever is higher priority will get the suffix, essentially. So if you get carboxylic acid in there, that will be the oic acid. That will definitely be, right? Yeah, so hopefully that makes sense. This priority table is really important. It's not that you have to memorize exact word for word. However, you need to have done enough practice questions overall to, like, essentially know this roughly. You will get to a point where essentially I guess, carboxylic acid, you will just straight up know that's the top one. After that, it'll be an ester. After that, it'll be amide, etc., right? I did see a question somewhere. Where is it? what do we call amides formed by condensation with carboxylic acid amide, where the CONH is in the middle of the carbon chain? We call them secondary amide, or something like N-ethyl ethanamide. Yeah. So basically the second one. So you don't, I guess, the N just means that you don't like necessarily to mention the locant there. So yeah, you call them the N-ethyl ethanamide if that's formed by condensation. We're talking about amide synthesis reactions later on using condensation. So yeah, awesome. Yeah, so N is for that locant. So normally you would have 3, 4, or whatever to name essentially where the carbon is, right? But in this case, it's just basically it's basically just something that you put in there just to be like, okay, we know where the locant is essentially, if that makes sense. Yeah. Does that make sense? Yeah. Okay. It just means hopefully that makes sense. But it just means where essentially the nitrogen is connected. Yeah. Kind of thing. Whatever that. Yeah. Okay. Cool. All right. Yeah. Okay. So this should be pretty straightforward. Now, so functional. So how you actually name it. So you obviously need the longest carbon chain, right? So if there is for example, a methyl group connected here, right? And there's a C here. You wouldn't go with this chain, right? You would obviously go with this chain. However, there could be, for example, you got 3 here, and you got sorry, not CH3, but CH2, CH2, CH3. Then you wouldn't go with the straight chain. You would go with this one because there's obviously 5 carbons in that one versus the 3, right? So that's very important. Longest carbon chain, that will be your, essentially at the end on determining if it's an ethyl, methyl, propane, propyl, butyl, etc. Right? So make sure you know all of those, by the way, the numbers, right? And then the number chain to give the lowest number to substituents, name and number branches and functional groups. That's pretty straightforward, using the prefix if multiple occurs, or suffixes, I guess, and use correct suffix for functional groups. So this one is important because that's based on priority, right? Cool. Alright, isomerism. So this is actually kind of high yield. There have been quite a lot of questions based on isomerism, but this is pretty straightforward to remember. There is a lot of other types of structural isomers and just isomers in general, but the two that we need to know is mainly structural isomers and stereoisomers, right? They do ask a lot of these questions, and I will give a bit of a tip later on. I'll just give it now, but after structural isomers. So what is structural isomers? Same molecular formula, different structure. Okay, so that is super important to understand the difference between that versus stereoisomers, which are same structural formula, but the atoms are just arranged differently, right? So for example, structural isomer, it could be we'll just go to a normal a butane, right? So what it would be a structural isomer for this, it would just be you go 3 and then you got a methyl group attached to that, right? Okay, this is a structural isomer, right? Why? Because you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, 4 carbons, and you've got 1, 2, 3, 4, 5, 6, 7 plus 3 there is 10 hydrogens and 4 carbons. So you've got the same molecular formula, right? But it's but different structure, right? So you have a metal functional group essentially added onto that, right? So you do have different ones, right? Chain isomers, position isomers, functional group isomers. I don't think you need to know this. This is just something that if you wanted to know. Essentially, chain isomers is where you have different carbon backbones, similar to what we just did. Position isomers, same groups, different positions, and then functional groups isomers, just different groups altogether, everything, right? This is a pretty high yield thing. Something to note, okay, if you cannot figure out a structural isomer from this, consider cyclic. Okay, consider cyclic carbons. So something like, cyclic hydrocarbons, right? So that is quite important to remember, because there has been a few questions in the external exams as well, where I'm not sure external exams, but definitely practice ones, that were you have to, the answer was an isomer that was a cyclic. So just keep that in mind, that cyclic is an option. And keep in mind that it is because it reduces the number of hydrogens that are attached to it as well, right? Okay, in terms of stereoisomers, right, this is pretty straightforward. You got same structure formula, atoms arranged differently in space, which just means like the 3D structure is different, right? Cis trans, in other words, geometric. So I'm pretty sure you guys probably know this as geometric isomers, but cis trans is the same thing, right? This is such an important point. That's why I've underlined it. Generally, throughout the PowerPoint, you'll notice underline, bold, and italicize. I do all those three formatting to essentially like make sure you guys remember that. But this has to happen over a rigid double bond. Okay. Why does a rigid double bond matter here? The reason why it matters so much is because that's what makes it a different compound. Well, different isomer, right? Because if you had that, and look, theoretically, right, if this wasn't, if it wasn't a rigid double bond, then having, a functional group on one side is, wouldn't matter that much, right? So, I don't have enough space in here, but if it was like this, right, and then you had, let's just say chlorine attached to it, right, versus C, and then you had a chlorine attached to this side, right? This wouldn't be different if it wasn't for the rigid double bond, right? Because it's so rigid, it makes it that putting functional groups on two different sides, alternating sides, make the actual isomer different chemically, right? So that's very important. Optical isomers, so I think you guys should know it as enantiomers. We call it an optical isomers generally in chemistry. This one is not too high yield, but this one's based on the fact like we know like squeal structure a little bit. But essentially, this is essentially where you have a chiral carbon, right? So maybe alright, I'm gonna rub. Oops. Yeah, I'm just gonna rub a few of these things out. So we have a little bit of okay, there we go. Alright. So go back to the pen. Alright. So and so yeah, basically based on, as I said, chiral carbon, which means like essentially whether you have it in front or back, right? So generally, right, we can have a structure. Let's just bring this, and you got A, B, C, right? You got three random functional groups attached to this, right? Generally, how we say chiral carbons is based on a thick, essentially thick arrow-looking thing versus a like dotted one, right? So essentially, the dotted one means that it's like the dashed one, right? Just means that it's going into the page, right? And then the thick solid wedge one is coming out of the page, right? So this is out of page, and this is into page. So this is kind of at the back, and this is at the front, right? Again, I do not think you need to know this. Like, I mean, even if you do, it's very, very low yield. They wouldn't ask you to do that. But one of them is back, one of them is front, and that's essentially, and the other one could be the other way around, if that makes sense. So, and then essentially this one could be, for example, like, yeah, let's just put this one, right? C here, and then B here, and an A here, and that's like a chiral carbon because it's changed now. So that's an enantiomer, right? So non-superimposable, what does that mean? That essentially means if you were to put these two and then put them on top of each other, they wouldn't be the same, right? That's what makes it essentially different. All right. Yeah, cool. So, and then, yeah, mirror images, meaning, so if you were to mirror something, right, like if you had a mirror and you got a mirror image of that, you wouldn't be able to put it on top of each other because they would be different. They would be different structures. So that's what it means. You do need to know about enantiomers. It could be like, for example, a multiple choice question. So that is important, but you wouldn't need to know what I just talked about. Probably you don't need to talk about that. Yeah. It is important though, because the structural differences do have quite a lot of like consequences in the chemistry world. So yeah, it is important, especially in terms of like drugs and stuff like that. In terms of like medicinal drugs. So yeah, it's very important. Okay, physical properties. This is actually quite high yield. Obviously, it seems quite important. But melting point, boiling point, solubility in water, right? These are incredibly important. It is almost bound to be in one of your external exams. Like it's probably going to be in your external exam. There's going to be a question about this. That is how important it is, right? But essentially, it's super important to know the reason why boiling point, melting point, and solubility differs between hydrocarbons or different compounds, right? And obviously we know them because of intermolecular forces, and obviously you learned these in year 11, so hopefully you guys have a good idea of it. But definitely on the type of it and the strength of the intermolecular forces is super important. Right. Okay. So speaking of which, let's go over a brief kind of overview. Right. So displacement forces, we know what these are. These are basically just anything that's not the other two. Right. They're in all of the molecules. Right. And they're basically the only intermolecular force in non-polar molecules. So generally, if you have a hydrocarbon like this, a simple propane, there's only dispersion forces. Right. So I know this is not a great, I guess, piece of advice, but if you have absolutely no idea to do, I guess, for intermolecular forces, chuck down dispersion forces, right? So if they're like, oh, what intermolecular forces are in this molecule, how does that, like, I guess, contribute to its melting point or boiling point? Just be like, there are dispersion forces. Hope for the best, I guess, but you probably wouldn't get a mark for that, but at least there's something down, right? So that's in everything. Dipole, this is very important. These are essentially partial poles that are attracted, right? So they're in, as you know, as the thing says, it's in polar molecules, aldehydes, ketones, because you have a oxygen. As soon as you bring an oxygen into the mix, that's already a imbalance in the electrons, right? Because it's such a highly electronegative atom. All right. Hydrogen bonding, our favorite. This is probably the most high yield 2 words in the QCAA, right? Hydrogen bonding. It is used probably across the whole syllabus somewhere, right? Whether it be, in the melting point, boiling point that we talk about now, or whether it be later on when we talk about protein structure, right? This is the most high yield word, hydrogen bonding, okay? So, it's literally basically strong intermolecular forces that are between this N, oxygen, or fluorine. Obviously, because it's hydrogen bonding, it's with the hydrogen. Remember phone, phon, which is phone, similar, right? F-O-N, fluorine, oxygen, nitrogen. Okay, that's how you remember the hydrogen bonding atom. Okay, so something to make it easy for you guys, because there is, again, bound to be a question on the intermolecular force and how it relates to it. Alkanes, alkenes, alkynes. These are hydrocarbons, just pure hydrocarbons, right? So they only have those London dispersion forces. Okay, and then you've got, oh wait, is that a question? Okay, and I know you might get to it, but I have a question about the between ourselves and myself lab mutually. Charge and a, so in a micelle after it clumps. Oh, oops, what just happened? Okay, cool. After it comes up too much on an oil, wouldn't the ionically charged head eventually just repel any neutral charges that try to come through to the oil since... Sorry, wait, what? So in a micelle, after it clumps up too much on an oil, wouldn't the ionically charged head eventually just repel any neutral charged things that try to come through to the oil since they have an ionic head? If you need to get to this later, okay. So, just talking about the micelle, right? So, micelle made up of lipids, right? So, it's a, clump of lipids. I will definitely get to this later, but, okay, you have a hydrophilic head, right? And then hydrophobic tail. So, are you talking about the specific hydrophilic head where it's ionic, right? Okay, actually I just realized that the chat's way too low. Okay, yeah, so so essentially, I'll just try and answer what I think that you mean. Oh, okay, yeah, I don't know. Okay, cool. So if too much polar heads on it, wouldn't the heads just all repel each other at some point, and stop more heads from coming towards the oil? That's the micelle can't fully form. Yeah, okay. This is a good question actually. So the charged heads, they form a head they form a shell around it. But it's essentially that whole micelle is stabilized, right? So obviously you do have them repelling each other, which is essentially why they don't, I guess, in a way form bonds with each other, right? But those electrostatic interactions form mainly between the water molecules outside, not with each other. They do repel, which is why it forms that structure, but they're very stable in that form, right? So technically, first of all, your first one, so neutral charge things, right? They don't carry any electrostatic charge, right? So they're neutral, right? So they wouldn't be repelled by the ionic heads, right? But the neutral molecules that you're talking about, they don't really, I guess, interact strongly with them electrostatically. So they can still diffuse through the water and interact with the micelle, but obviously you don't see them like, repelled by the charge, because obviously there's no charge of a neutral, like a neutral molecule, if that makes sense. Does that kind of answer your question? Or, so you'll have to edit that message again, sorry, because like the chat is way too far down. Does that kind of make sense? But yeah, that is a good question. Yeah. Yeah, okay, awesome. Yeah, cool. Thanks. Okay, yeah, that's awesome. So yeah, just to summarize that question for everybody else as well. So basically, neutral charged molecules obviously won't be repelled because they're neutral charged. So and there's ionic heads which obviously wouldn't interact with them. And then in terms of like, I guess, can the micelles, I guess, be blocked in a way, right? Because of the like repulsion between the other polar heads. They can happen, but it is stabilized, right? So they're like what I forgot the exact word, but they're called self-limiting, right? So if they're all like similarly charged, they'll naturally repel each other, but like that will like there'll be a limit of how many like molecules can pack into a single micelle. It doesn't really do anything else, right? So that'll only just limit the size of the micelle. That's it basically, right? But yeah, I will talk about micelles later on in sponification and all that. Cool. Okay, and just going back to this, so dispersion force is only for these ones: alcohols, carboxylic acids, amine, hydrogen bonding, because of the oxygen nitrogen in them. So this is very, very high yield to remember, or no, it's not even remember, just know these, right? And you got aldehydes, ketones, esters, which would dipole. And the reason why they have dipole and not all, I mean, they do form weak hydrogen bonds depending on what you are, I guess, bonding with. But generally, when you're talking about hydrogen bonds, you talk about intermolecular, so within the same molecules. So generally they don't, because they only have a oxygen tightly double bonded to it, right? And in halides, dipole dispersion. This makes sense, right? Because it's with halogens. Cool. In terms of alcohol, okay, so now we're just going through the intermolecular forces in depth for each of the functional groups, right? So in terms of the boiling point for alcohol, so obviously there's a few specific information here, so you don't really need like to know the exact like temperatures and stuff like that, right? But what you need to know is relative to other ones and why. So they're much higher than normal hydrocarbons, right? Because of the hydrogen bonding. That's super important because you've got that hydroxyl group, right? Any interaction with another hydroxyl group is super important, right? And then the other way around as well. So for any carboxylic acids and anything else, right? So, and that just increases with the more hydroxyl groups you have. So the more you have, just the more boiling, more hydrogen bonding that occurs, right? Okay, volatility. What is volatility? For anyone who doesn't know, that's just essentially opposite of boiling point, right? So if you have a lower boiling point, it is more likely to vaporize, right? So what does vaporize mean? Not what vaporize mean. What volatility just means the more likelihood of vaporizing. So if it has a lower boiling point, higher volatility, right? Higher boiling point, lower volatility. So alcohols, as you can imagine, like for example, like even like fuel and stuff, right? If you drop it on the ground, you can see it vaporize quite quickly. It only stays there for a bit, right? So this has essentially low volatility because of the very high temperature, right? So so this is very important. And diols trials, remember what those are? That's just basically 2 hydroxyls, 3 hydroxyls. Okay. Cool. Does that make sense? All right. And in solubility. Oh, thank you. I appreciate that. I'm sure if you watch Ashan's one, it is equally good, if not better. So, yeah. He went for like a solid 4 hours or something like that. So, I'm sure you've maybe not have watched this one, but it's very good. So, yeah, anyway. Solubility. This is very important. Solubility is mainly based on the fact of the functional groups, right? So, alcohols, what are they? Very polar, right? They have literally a hydroxyl group in it, right? Just similar to, right there. There you go, right? That's water, right? So, see the difference? Yeah, right? So, Actually, not see the difference, see how similar they are, right? So solubility wise, so these are very, very soluble in water, right? So, and you can imagine, because hydrocarbons, so if you have, say, boom, 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 right? And then you've got OH here, right? That is much more soluble than obviously something without it, right? Something with just hydrogens attached to it, right? Okay, because obviously you don't have the hydroxyl group anymore. So essentially what it's saying, solubility decreases as hydrocarbon chain increases. So the longer the hydrocarbon chain, right, the less soluble it is, right? However, it is soluble in organic solvents, right? So soluble in organic solvents is just anything that we've been talking about so far, so hydrocarbon related stuff, right? Cool. Alright, so that's alcohol. So this is very high yield. Aldehydes, ketones, carboxylic acids are very high yield too. So, but I'll just quickly go back to aldehydes and ketones. So in terms of aldehyde and ketones. Okay, so remember this is the carbonyl group, right? Carbonyl group for aldehydes in the terminal carbon. Ketones are just, anywhere else but the terminal carbons, right? And so boiling point wise, higher than alkanes. So basically a lot of things would have higher than alkane, right? Because it has dipole-dipole interactions, unlike alkanes, which just literally just have dispersion forces, right? So alkanes just dispersion, right? Whereas you have the aldehydes and ketones, which have the dipole-dipole interactions because of this very highly electronegative oxygen that you have, right? But obviously it is lower than alcohols, because we just talked about alcohols had a very, very high boiling point because of the hydrogen bonding, because of the hydroxyl group, right? Now this is actually very important because both of them have oxygen. So what's the reason behind this, right? It's purely because of the double bonded oxygen versus the hydroxyl group. So the hydroxyl group essentially gives a lot of that hydrogen bonding, right? You can still form potentially under the right conditions hydrogen bonding in carbonyl groups, but it's very weak hydrogen bonding, if anything. So hydroxyl groups are very important for that. So because they don't have a hydroxyl group, there's no, basically just assume for now there's no hydrogen bonding, right? More volatile than alcohols because of the lower boiling point, right? Lower boiling point than alcohol, so it's more volatile. And then you've got moderate boiling points. So it has roughly in the middle, so 49, 56. So as you saw in the previous one, propanol, which is 97, so very high boiling points, right? Cool. And then solubility wise, it is obviously somewhat soluble with water. So yeah, I guess you do have that like interaction going on there, but yeah, this is not as important, I would say. Alright, carboxylic acid, so again, another high yield one. So alcohol and carboxylic acid, very high yield. So carboxylic acid wise, the boiling points are very, very high, right? Strong hydrogen bonding dimerization. Dimerization, what does that mean? Two molecules of the same thing, right? So carboxylic acid forms dimers with itself, essentially. So that becomes a dimer. So say, for example, O2, right? That formation is called a diatomic, right? So that's a dimer right there, right? So, but yeah, dimer in this case is like for carboxylic acids via those hydrogen bonds. So that's a very high one. As you can see, 118 degrees, and that makes its low volatility because of the incredibly high boiling point, right? So carboxylic acids, or COOH, then you've got the OH, then you've got these guys, right? So that's kind of how it goes. So yeah, volatility. Yeah, so it's essentially the ability for it to essentially vaporize, right? So in other words, like if you have a lower boiling point, right, it's much easier for it to vaporize, so turn into gas, right? So if you have a very low boiling point, very easy. So yeah, that's essentially what volatility means. Cool. Yeah, that's good. Okay, so that was a very quick summary of topic 1. Obviously there is, so okay, this is a very important thing, a very important, I guess, point to make really quickly before I go into topic 2. I'm just going to turn my camera on briefly as well. So very important point to make. The stuff that I covered in topic 1 are everything separately. So functional groups separately, the naming of stuff separately. When we'll do a little bit of questions later on, but when you do questions, everything will be combined together as one question. Okay, they're very, unless it's a multiple choice, and they will give you a short answer like just name this compound, but it'll be in the context of a much bigger question. So topic 1 is primarily like nomenclature, learning the basics, but you'll basically never get them asking just for the basics, like, oh, what is the boiling point of carboxylic acid, or is the carboxylic acid boiling point higher than alcohol? You're going to have to explain this whole thing in the context of everything, which is why I'm going to give you like a bit of advice later on in terms of, I guess, doing the questions in terms of melting point, boiling point for carboxylic acid, because, and homologous series even as well, because it is a very high yield. A lot of questions come on that. Alright, that's an important point to make. That's why I was so quick topic 1. Alright, yeah. Now we've got topic 2, which is a gigantic topic. Chemical synthesis and design. Alright, okay. So as you can see, right, I'm just going to go through a lot of these, right? Boom, boom, right? These are just a ton of like slides about a lot of the reactions that you need to know, okay? So just keep in mind, you need to know these reactions. However, I know it's probably a little bit more than a week away. The reaction conditions, you probably want to know. I think next year, for example, like the new syllabus, I think you don't need to know. I've been told that you don't need to know the reaction conditions and stuff. However, for this, you would probably need to know reaction conditions, but I mean, if at this point you don't have them memorized or you don't know, I wouldn't spend like an enormous amount of time trying to memorize them, okay, if you don't know them already, because it is quite extensive. Alright, now we'll talk about addition reactions. Okay, addition reactions, super easy, right? These are probably the easiest types of reactions you'll see. It's just double, triple bond, unsaturated. What does unsaturated versus saturated mean, right? Unsaturated means it has a double bond or a triple bond, right? That's literally it, because it has the ability to have more hydrogens and be more saturated with hydrogens, right? So this is not saturated, and obviously there's hydrogens by the connecting to it, but I'm just not going to bother. This is saturated, okay? Because it has all the hydrogens connected to the carbon chain, alright? So very straightforward. So essentially what this does is convert those unsaturated, so the ones with double or triple bonds, into saturated ones. These are a very important concept to do, because we also look at other ones like elimination reactions later on. Okay, so first type of addition reaction. Now I'm going to kind of more or less rapid fire through the next few, because these are quite easy. Hydrogenation, very easy, adding hydrogen, okay, hydrogen gas, hydrogenation, addition of hydrogen, okay. This is again, oh, whoops, what just happened? Alright. Okay, hydrogenation, okay, sorry, go back. So, this is the addition of hydrogen, and as we mentioned, what is the definition of addition reaction? It is literally by the double or triple bond, so it needs to be added on a double or triple bond. So as soon as you see a molecule with a double or triple bond adding hydrogen, it's going to be an addition reaction, okay, because there's nothing else, basically, that can't be, right? This is, again, the condition, so catalyst is required, so generally the platinum, palladium, I'm pretty sure nickel, right? No heat required, right? This is kind of important, because the three things reaction conditions-wise you're going to get is either a catalyst, right, heat, pressure, and if it's a catalyst, sometimes it's acidified. Sorry for the bad handwriting, but acidified over something, right? So yeah, just keep that in mind. But this one is no heat, just catalyst. Hydrogenation of, oh yeah, this is just an example, something cool that I, knew. So hydrogenation of vegetables to make margarine. Yeah, that's about it for that. Okay, halogenation, again, very easy. Halogen, you add a halogen, so chlorine, bromine, iodine, fluorine, right? All those ions. So you add one of those, right? Oh, sorry, not one of those, but the two, because obviously they come in twos. So essentially you get oh, this is wrong. Sorry, that's not supposed to be there. Yeah, that's obviously, yeah. Okay, but yeah, this is pretty straightforward, halogenation, because you just add, as I mentioned, the halogens across these. Cool. So that one is about halogenation. Okay, yeah, this is actually quite high yield. So super high yield is the bromine water test. Okay, if you didn't listen to this whole thing, probably want to listen to the chemical test here. Okay, they use this quite a lot, especially in like when they like tell you, okay, this bromine test, it turned it stayed colorless or turned like orange or whatever. Sorry, it turned colorless the other way around. and then they're like, oh, what does this mean, kind of thing, right? So essentially, this is where you add bromine, which is a halogen, right? This is where you add a bromine, and it's essentially to test whether a hydrocarbon is essentially saturated or unsaturated, right? Okay, saturated, again, remember, means boom, saturated means boom, right? Okay, so how does this work, right? The bromine, like the actual bromine, is orange, right? What they use is orange, right? So halogenation, what does it happen? Happens over a double or triple bond, which means it converts to a not double or triple bond. So for example, all right, we've got ethene, right? And that if you add a chlorine, like let's just say if you add a chlorine to that, you'll get this, right? The chlorines add. So you remove the double bond. Okay? So if you remove the double bond, that means you no longer have, that means like the bromine's reacted, right? Or whatever the halogens reacted. So if you add an orange, if you add, what am I saying? If you add a bromine to a double bond, right? That will become a single bond, right? And it will lose the orange color, right? Okay, so the color disappears. That means you've added it across the double bond, right? Which means the hydrocarbon that you just added was unsaturated, okay? But if it does not disappear, that means there hasn't been a double bond or triple bond to interact with. So it's probably been added to this, right? If you add bromine to this, nothing will happen. So therefore, it will stay the same orange color, okay? So this is essentially if it's an alkane, right? Then nothing will happen. The color will stay the same. This is a pretty high yield one. They'll ask this in the context of a bigger question. So they'll bring the bromine test, they'll bring the oxidization test, which I'll talk later on as well. They'll talk about all of these to determine, different ones. Okay, very high yield. All right. Okay. Mid yield. All right. So notice high yield. Honestly, this is probably high yield too, but I just put that there. Okay. Let's talk about hydrogenation and then to talk about Markovnikov's rule. This is not actually too difficult, right? Pretty straightforward. But let's talk about hydrogenation. It's just adding a hydrohalide. What does that mean? HCl, HBr. It's just a hydrogen connected to a halogen, which I've just put there. So it could be HI, right? HF, which is a very strong acid, I believe. Yeah. And then HCl, HBr. Right? Those are all hydrohalides. And you're adding that across the double bond, right? So Markovnikov's rule. What is Markovnikov's rule? This is very important. It's by this Russian dude, right, who essentially made this rule up because he saw it happen, right? So essentially, what happened is propene. Let's just go with propene. This is the very typical one that you'll probably get, right? You add HCl, right? Essentially, when you add HCl to this, you will get two products. Okay, one product will be where you add, if you have the propane here as normal, and you'll add it to this carbon, and I'll talk to you about this later on, not later on, like right now. And then the other chlorine will add to this. Okay, now this probably will be high yield if I put the hydrogens on. Okay, so what's the difference between here? All right, what he sees is when he added the hydrohalide to the HCl, right, the hydrogen atom with essentially bonded with the carbon with the most hydrogen atoms. So generally the one in the like essentially the one on the end of the chain. Right? Does that kind of make sense? Yeah. Okay, cool. Okay, yeah, anyway. Okay, so yeah, hopefully that is. Okay, so yeah, it's the one that essentially bonds with the, so yeah, again, we're doing that, right? When you add the hydrohalide, so HCl, HBr, everything like that, the hydrogen atom in that hydrohalide bonds with the carbon with the most hydrogen atoms, right? Generally, which is at the end of the chain. Okay? So, okay, perfect. And that's just basically named as Markovnikov's rule. Right? Okay. So, essentially the ratio 90% main product 10%, not main product. I don't think you need to know that. What we call it the anti-Markovnikov's product. Okay. Cool. Alright. Hydration, yeah, also kind of important because we talk about hydrolysis later on, which is the opposite of that. Well, it add water to break down, but this is add water to, make something. I love this one because it has everything in terms of reaction conditions wise. It has everything: temperature, high pressure, and you have a strong acid catalyst there. Okay, so generate phosphoric acid, for example. And okay, yeah, additional water, that's pretty straightforward. When you hydrate, you're adding water to your body. So yeah, if you add, hydration is the form of adding water to the double bond, and it forms alcohol. So if you want to see that, right, ethene, that's not supposed to be there. Then you add water, so H2O, or in other words, HOH, right? So what will happen is you got boom, 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 right, OH. Right, the other H, if you're wondering, came onto these guys, right? So that forms an alcohol. Alright, so that is very important. Yeah, and again, very easy to remember hydration because literally all of the reaction conditions are there. So high temperature, high pressure, strong acid, generate phosphoric acid. Okay. Okay. Super high yield. I forgot to put the high yield button here. Polymerization. Okay. Generally, actually, when they do this, they probably bring up like when they put hydrocarbon organic chemistry questions. They do quite a lot of polymerization ones. I will talk about polymerization again later on, so keep this in mind. But this is called addition polymerization. Very important to know. This is addition polymerization. Okay, I'm going to repeat that again. Okay. So this is essentially where you add a ton of alkene monomers to form long chain polymers. Okay, so those polymers obviously remove the double bond, so you get a saturated non-double bonded polymer at the end. Okay, again, very good reaction conditions: high heat, high pressure, and catalyst. Okay, so similar to hydration, you just have everything. Catalyst, you don't really need to remember, just high heat and high pressure is the main one. Right? Self-addition is very important because you just essentially add it like ethene to itself, becomes polyethene. You add, propene to itself, polypropylene, polypropylene technically. Chloroethene, you add it gets polychloroethene. It's just you just add the poly in front of it kind of thing. So just to reiterate that, right? So if you have this adding to another one of this, right? What do you get? You get this removal, you have an extra bond, right? So if you remove this bond here, you have an extra bond, right? So this bonds with this one now. So essentially you get boom, boom, like that. And these bond to the next one, but you don't write that. And you put an N. Very important to remember N. Okay, because that just means it's a polymer. Okay. Yeah, and this is just called a polyethene. Okay. So, actually, maybe I'll mention it now. Something to mention. Actually, no, I wrote it here. Polypropylene versus, and this some people call this polyethylene, right? These are the same thing. Polypropylene is polypropene. However, please use polypropene. Okay, that is the IUPAC name for a polymer that's made of propene molecules. Okay, polypropene. Polypropylene is just like, kind of like a not really colloquial, but like, what the non-chemists use, and hopefully you all consider yourself very expert chemists. Okay, so yeah, that's it. So polypropylene, do not use polypropene IUPAC name. Alright, that's just a good thing to remember. This is PVC, by the way, chloroethene, polychloroethene. So whenever somebody brings up PVC now, like PVC pipes and stuff, you can be like, that's actually made up of a chloroethene molecule. So yeah. Alrighty. Let's check the chat for a second there. Alright. Ton of pressure, I'll talk. Fair enough. Damn. Mini pepper. Alright, fair enough. Alright. Yeah, real. Mega Knight. No, that's mid-ladder stuff, guys. Alright. Joking. Okay. So, elimination reactions. Alright, this is very important. So, elimination reactions, just think of it as opposite to addition reactions. Okay? So, groups are removed and it forms a multiple bond, which is as we know, of course, it's probably a double bond. We just love double bonds here at the moment. Okay, so something is removed to form a double bond. Remember, what are addition reactions? You add something to remove a double bond. Okay, so it's like literally this exact opposite. Okay, so yeah, okay, and this is usually pretty like there's not much to it, right? So it's generally for if you were talking about haloalkanes, for example, it removes the halogen atom from one of the carbons, or the hydrogen atom from the carbon adjacent to that one with the halogen. So that's pretty straightforward. I mean, I'll quickly give an example as well. Maybe we'll go with a just keep it simple. So we go Br here, right? And then that will essentially, what we do is form a double bonded, so we'll form a propene molecule, right? And then you'll form some extra. So I think it's usually like NaBr, because you add a alkaline to that, or base, sorry, and then you get water as well, right? So conditions wise, reflux, it's essentially done under reflux. So what does reflux mean? Essentially, it's like where you have an apparatus where, like, you have conical flask, they heat it up. So this is a fire, heat it up. And what happens when you heat up a liquid? It turns into a gas, and they catch the vapor, and then essentially when they catch the vapor, they chuck it back into the flask, right? Sorry, yeah, this is not a conical flask or whatever. Yeah, sorry. But yeah, essentially, it's just yeah, it's just basically you don't lose any stuff, you don't lose any reactant. Okay, you just chuck it back inside the reactant and make it reactive again, essentially. And then, yeah, strong base dissolved in ethanol. That's just something to memorize, unfortunately. Heat to favor elimination of a substitution. Okay, why? I'll tell you guys anyway, but really nobody cares. But essentially, with the higher energy, because elimination reactions generally require a very high activation energy. You're literally creating a double bond, so you need a very high activation energy. So because of that, when you put in a ton of heat, it will become a elimination over substitution reaction. Okay, right, yeah, thank you guys, thank you, I appreciate it. The flask does look quite beautiful, and thank you about caring about the heat added to that. Alright, oxidation. Alright, let's talk about this, and I really hope you guys know this, because we know the goat already told you, Ashan, right? We told you what oxidation redox means in the last unit 3. I'm sure he went over it a ton, right? So this is, as it says right there, it's quite high yield, right? Super high yield, quite very important, right? But let's just go over it in a few seconds. Oxidation, loss of electrons, right? So remember oil rig, or what's the other one, like Leo goes girl or something like that, right? There's a few mnemonics you can do that, but oil rig is usually the one. So oxidation, loss of electrons. This is the best way, so to know it, right? In I guess, practically speaking, it's a gain of an oxygen or a loss of a hydrogen, right? Why? Because when you add an oxygen, so electronegative that it takes the oxygens, right? And this is a loss of an oxygen, or gain of a hydrogen is reduction, right? Redox, what does redox mean? It just means happens together, right? And again, Ashan has told you that already. Alright, high yield stuff now. Oxidation of primary alcohols, very quick. You have primary alcohol, secondary alcohol, tertiary alcohol. If you oxidize a primary alcohol, it will go to an aldehyde. Okay, you know what? I'll just go this out. Okay, so boom, 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 with an OH, right? If you, again, I'm just not drawing the H's here. If you oxidize this, what will happen? You'll turn into a aldehyde, right? Okay, so it will become a hydroxyl group to an aldehyde group, or like a carbonyl group, basically on the terminal carbon. In other words, it's an aldehyde group, right? And then when you oxidize this again, right? Or just keep in mind, you lose 2 hydrogens. So you lose the hydrogen here, and you lose the hydrogen here, right? So there's a loss of hydrogen. Remember, that is an oxidation, as we defined earlier. When you oxidize this again, one more time, you'll turn it into a carboxylic acid group. So you go like this, and then oxygen OH. Okay, so what happened here is basically you've got a gain of another oxygen. So this hydrogen technically stayed because you've got the hydrogen there, but you've added now not that oxygen, you've added this oxygen extra. So now you've got another oxygen atom, which is again definition of an oxidation. Okay, so that's primary alcohol, very important. Primary primary, only a primary alcohol, and we'll talk about this next, okay, secondary alcohol next, but conditions-wise, potassium dichromate, we'll talk about this to death in the testing section soon, but potassium dichromate acidified with sulfuric acid, you just need to remember that, and it's warm to like a mid-temperature, like 50 degrees, right? Alright, oxidation of secondary alcohols, okay? Secondary alcohols is where it'll become a ketone, okay? So you have a secondary alcohol, so let's just use the previous one, similar one, right? Okay, and then if you oxidize this, what happens? We'll have the loss of 2 hydrogen atoms, as I also say that wrote there as well, so that will be like this. Okay, so this is a carbonyl group that's now within the chain, not on the terminal carbon, okay? So that means that it's now a ketone, okay? Now, question is, why does it stop there, alright? Why is there no further oxidation possible? Because if we, theoretically, right, I mean, this is not even theoretical, it's like, you know, impossible, but if we were to oxidize this again, right, to a carboxylic acid, this is impossible. You've literally got 5 bonds there. You got 1, 2, 3, 4, 5. Remember, carbon will never make 5 bonds, so this is a big no, okay? Ketone is the end of the oxidization of a secondary alcohol, okay? Okay, cool. And then, oxidation tertiary alcohols, yeah, that does not happen. You cannot oxidize a tertiary alcohol, as you can imagine. You do not have any carbon bonds to do that, so it cannot be oxidized. Which brings us to the high yield testing, chemical tests, okay? Potassium permanganate and potassium dichromate, okay? These two basically, I mean, not basically, they do the same, this exact same thing, alright? So, why is this important? So, okay, like color change, purple to colorless, so, very important. It gets reduced to M2+, which is colorless, right? So, but essentially the I guess, what do you call it, the theory behind it is, can we not see the PowerPoint? Yeah, okay, cool. Oh, really? So some people can see it, some people can't see it. Okay, most people can see it, it seems like. Okay, yeah, right. Sorry, there's probably like a ton of stuff happening. And the other thing is that, like, my server, like my Nitro is on my laptop account, and the iPad account doesn't have Nitro, so I think it's streaming on a less quality as well. But I mean, look, that probably makes it worse anyway for you guys. Anyway, if it was a high quality. Alright, anyway. Okay, keep continuing with this. Okay, so if you have an oxidization, so this isn't something that will oxidize. So as I mentioned, that was part of the reaction conditions here. So the potassium dichromate, same thing here, potassium dichromate. So when you put this into a primary alcohol, it'll turn into a carboxylic acid, right? Or if you put it into a secondary alcohol, it'll go to a ketone. And then if it's an aldehyde, it'll go to a carboxylic acid, which is obviously like a, you know, intermediate between the primary and the carboxylic acid, right? So essentially, how is this a test? If you literally chuck a tertiary alcohol and you put this potassium dichromate into the like solution of, I guess, yeah, the tertiary alcohol, there should be no color change. Okay, so that means there is a tertiary alcohol in there, right? And the primary alcohols, right, that oxidizes twice, right? And secondary alcohols only oxidize once. So if you want to distinguish between the primary and secondary alcohols, you need to oxidize the alcohol to an aldehyde or a ketone first, right? And then decide if you have an aldehyde or ketone, then you will essentially need to test whether the compound can be further oxidized to a carboxylic acid, because ketone again won't be oxidized to a carboxylic acid. Okay. Last one, probably important, is the aldehyde test, which is a Benedict's reagent or Benedict's solution, whatever you want to call it. This is basically similar, but essentially with aldehydes, it's generally blue, but then because copper sulfate is blue, we should probably all know that copper sulfate is blue, and that will essentially get reduced to copper oxide, which is essentially a very bright red precipitate, right? So yeah, so this is essentially for aldehydes, because it gets oxidized, it will turn red. With ketones, there's no change, right? Okay, yeah, this is, I just wanted to, I don't want to confuse you guys more, but ketones can be oxidized under these mild conditions. The reason why I wrote mild is basically under, like, theoretically, anything can be oxidized. Theoretically, right? Anything. It's similar to the fact that a piece, like, anything can be conductive. It's just more or less some things can be more conductive than others, right? Like, literally a piece of wood could be conductive if you have enough electricity going through it, right? Similar to here, if you have like a strong enough, thing that oxidizes it, then it should be, right? It should be able to oxidize. Okay, cool. Oh yeah, no, sorry. Like, yeah, I've mentioned at the start, I did not change the the syllabus points at the bottom of the PowerPoint because there are literally a ton of like syllabus points. So I'll probably be here tomorrow as well if I was copying them in. There's literally a lot. So yeah, that's probably not a good, I guess, confidence to you, but that's okay. So yeah, cool. Question. Is there anything differentiating the chromium and potassium? Yeah, that's a good question. Yeah, they're basically same purpose. They're just two different like oxidizing agents. So I think as a few mentioned there, the main thing is the color. So potassium permanganate is purple, right? And then it reduces to a brown. Yeah, I'm pretty sure it's brown. Yeah, purple to brown. And the potassium dichromate is essentially orange, which goes to a green one, right? So it probably just depends on like a few of the reaction conditions that they have, and yeah, exactly, like people have copied them. Yeah. Oh yeah, sure. It's basically the same. Yeah. So in terms of the Benedict's reagent, yeah, I'm pretty sure that was the question. It's very like it's exactly the same as everything else. It's just that the difference. Okay, the only difference basically is the fact that if it goes from blue to bright red, right? Because generally copper sulfate is always blue, right? But when it's reduced, it just turns into a bright red color, right? And it's in a precipitates essentially into the it's a solid state. That's basically the only thing. So aldehydes, if they're oxidized, they'll go into the carboxylic acid group, and then, well, not if they're oxidized. When they are oxidized, they go to the carboxylic acid groups, and they'll turn that bright red color. Whereas ketones, nothing will happen, so it'll stay that blue color. Cool. Okay, so that is the reactions, the testing. This is more or less, it's not really like high yield, it's kind of not that important, but combustion, right? So anything like fire related, right? So if you have a fuel, generally propane, and you have butane, right? I'm sure you've heard of them. Octane, right? That's generally the ones that we use for our cars, right? You have 98 octane, 95 octane, 94, technically 94 octane because that's ethanol with it. So all of that is basically fuel. You chuck it with oxygen, which is what again happens in a car. You chuck fuel, oxygen, and you chuck a spark, boom, fire, right? In this case, it burns to CO2, H2O, and heat, right? So this should be very, very, obvious. It's a very highly exothermic reaction because it releases a ton of heat, and it requires an excess oxygen. So if there's no, and I think you learned this in year 11, but if there's less oxygen, so if that's like the limiting reagent, you'll get an incomplete combustion reaction, which is essentially instead of CO2, it forms carbon monoxide. So yeah, cool. Alright, there are reduction reactions now that we need to talk about. This is like mid-yield as well. This is kind of like, I've seen this come up quite a bit. In terms of the highlighted, this is probably the most important reducing agent that you need to know, right? Lithium aluminum hydride, this is probably the biggest one, as I mentioned. So again, reduction, gain of electrons, gain of hydrogen atoms, or loss of oxygen, right? So reduction of alkenes, super low yield, probably just like, procrastinating this time, but it's like basically hydrogenation, addition of a hydrogen across that double bond, converts an alkane. This is just in your reaction pathway. That's just, you just need to know that that's a reduction. That's basically it, right? Nitriles are probably where you probably need to know a little bit more about. So you have a nitrile, so let's just say you have an R group connected to that, right? So just basically what I wrote there, the nitrile group. You essentially reduce this over the Li lithium aluminum hydride, and that just forms a primary amide, so which is RCH2 NH2. Alright. And then this one is, as I mentioned, the lithium aluminum hydride. However, I guess you could use the hydrogen gas or a metal catalyst to do the same thing. So as I mentioned, you can use the other reagents. So yeah, that's probably something too important to know. Alright, high yield. High yield. Alright. Who doesn't love a good esterification reaction? Condensation. What's this? Do you mean of the image? Like the image that person put there? Or for last part, what side? This one? Yeah, okay. For this one, do you need to just know one of them? Yeah. Just remember lithium aluminum hydride if that's what you're talking about. Like the reducing agents wise. Like just remember the lithium aluminum hydride. That's the most high yield one that you need to know. So yeah. Okay, cool. In terms of, coming back to condensation reactions, I'll be honest, this is my favorite reaction. It's really cool. Esterification, formation of an ester, right? That's pretty straightforward. Okay, that's what's called esterification. Okay, what is it? Carboxylic acid. So let's just draw one of those boys out, right? Boom, right? This is a carboxylic acid. Carbonyl group, hydroxyl group, combine carboxylic acid. You add this to an alcohol, right? I'm just going to draw the hydroxyl group on that side because, it's combined, right? What happens? Okay, condensation. What does condensation mean, people? Alright, this just means removal of water. Okay, what happens when you condense something? Water goes, right? So water leaves this, right? Water leaves the chat. Okay, so what happens when water leaves? You've got Cr, and then you've got something just chilling here. You've got an oxygen just chilling here, and then you've got hydrogen. Oh, sorry, not hydrogen. That also leaves. Technically, you've got the R group here, right? But let's just say C and then R, just for the sake of it, all right? So essentially, what happens here? There's a bond, all right? So that is removal of water to form an ester, all right? What is the suffix for this? OH, okay? So this is a ester plus water as a byproduct, okay? So in terms of the example ATP, hopefully people who do biology will definitely know. Adenosine triphosphate is literally the energy of our body, right? Basically, you don't need to know this, by the way. This is I'm just doing that for a fun fact kind of thing. But essentially, phosphoric acid plus alcohol makes an ester, which is basically ATP kind of converting between ADP and AMP, all that stuff. But yeah, it's essentially what I'm trying to say there is that it's a very important reaction, esterification overall. Okay, so esterification, good. I'll come back to, wait, do I talk about, okay, wait, no, do I talk about that? Okay, no, maybe not. Alright, so, okay, amide synthesis, basically, formation of an amide, like, what else would it be, right? But, what does this mean? Basically the exact same thing as I talked about. Okay, let's draw an amide out. Let's just say simple amide, right? Oxygen, right? With an OH, so that's a carboxylic acid. Well, sorry, if I said amide, but right. And then let's draw the amide, right? Sorry, amine. I don't know what I'm saying at this point. So yeah, you got the amine here, right? Right, it creates amide. Okay, formation of amide. So this is an amine, just to keep in mind. Okay, this is a carboxylic acid, which I'll show the carbs, right? And then again, water leaves because it's a condensation reaction. It's a type of condensation reaction. Okay, so water leaves. What happens is you've got a amide. What is an amide again? It's a nitrogen that is connected to a carbon with a carbonyl group. That is what an amide is, with a D. Okay, so that is an amide synthesis reactions. Okay, keep in mind condensation. Well, not condensation. I'm just going to talk about these two. These are all reversible. Can somebody in the chat say, how do you think you can reverse this? I talked about briefly earlier. Yes, beautiful, hydrolysis. Thanks, Mars. Alright. Yeah, hydrolysis. So you add the water to break it down. Okay, that's very straightforward. Because if you lose water to essentially form it, right? But then you add water to break it down. That's pretty straightforward, right? So yeah, awesome. kind of low yield red litmus paper. I just wanted to bring it in because I guess it is like maybe something if you want to know it, but considering it's a bit more than a week left, maybe not. But essentially, this is specific for amide synthesis reactions. Essentially, you can see when the red litmus paper turns blue. So depending on how fast or how slow or how much blue or red there is, you can still see if there's amine present in that, like the amine reactant, if the reactant is still present in that solution, basically. So, yeah, not important, but yeah, I just brought that in. Do I talk about... Okay, so I do not talk about substitution reactions, guys, by the way, because I just wanted to put that out. Substitution is something you should... Because I just took it... didn't talk about it because of... because time-wise. But it's, you do need to know about substitution, especially the halo alkanes ones. And, this is where primary... Oh, yeah, sorry for the people... for that person who asked before about primary, secondary, tertiary halo alkanes. But I did answer the question. You do definitely need to know it. And that will be in terms of the substitutions. I just didn't, just didn't talk about it today. It isn't important though, so definitely, I'll write it somewhere. I'll write it here, right? Substitution. Maybe if you have time at the end, maybe I'll come back to this. Okay, cover substitution reaction, guys, very important. I think that was in a few practice questions I remember doing. All right. Okay. Oh yeah, perfect. So this question, kind of high. So, okay, what do you guys think? This should be pretty straightforward. This is actually from an external exam. I think this might be 2021. Yeah, this one should be pretty straightforward. Essentially, you have polypropylene. Oh wait, sorry, backtracking really quickly here. Condensation reaction, something super important. Condensation polymerization. Okay. There are two types of polymerization, well, two types that you guys need to know. Addition polymerization, which we talked about before, where you add the same, like self-addition of the same reactants. And then you've got condensation reaction, which is essentially a formation of, like, multiple monomers, but it's combined through this condensation format, reaction, okay? So, this is an example, okay, that you can see here. Okay, PET. That is a polymer formed by monomers of carboxylic acid. I did my IA3 on this. Difference between addition and condensation reactions. Addition, polymerization, condensation, polymerization. So it is kind of high yield to know the difference between those two. Alright. So this is PET is formed by the monomers carboxylic acid and alcohol, whereas polypropylene, as we talked about, polypropylene, is formed by addition, right? So, okay, this is straightforward. What is the carboxylic acid monomer? Hopefully you guys can see that. There is a beautiful double bond O there. So that means this is your carboxylic acid. So that would be C, double bond to, and that's the carboxylic acid group. You got your nice benzene or your aromatic hydrocarbon there, connected to that, connected to that. Okay, that is your carboxylic acid. It's a little bit trippy just because there are two carboxylic acid groups on both sides, so you'll be like, wait a second, does this exist? But it actually does. Yeah, cool. And then, so this is your monomer for your carboxylic acid monomer, and then your alcohol monomer will just be the other section, but with the OH group connected to it. So you got OH, CH2, CH2, OH. So again, it's a bit trippy because you've got both on those sides. Okay. Oh yeah, sorry, this is supposed to be them. There we go. Where was it? I swear I saw some question. Do we have to include the benzene for part A? Yeah, definitely. That's part of the carboxylic acid monomer. I swear I saw another question. Oh, how the hydrogens come at the end. Oh, no, so they're asking for the, they're asking for, like, the reactants, the monomer. So, the hydrogens, like, they don't, like, this is the original reactants, and then they get formed by removing the hydrogens. The H2O goes out, and that forms together. That's just how it works. So this is the reactants we're talking about. It's not like a formation, like nothing's being formed here. Well, we're trying to figure out the reactants that form the actual polymer here. Alright, cool. That should be pretty, hopefully, I don't want to stress you guys out, but hopefully pretty straightforward, right? Thing we're discussing there. Alright, So now we're getting into a bit of the macromolecules, the organic molecules, right? These are pretty high yield, right? These are pretty high yield, so listen in. I mean, to be fair, this whole PowerPoint has been high yield because I'm not going to add every single little bit of information, little information there, so I've only added the pretty high yield ones. Okay, carbohydrates. What are carbohydrates? Carbo is carbon. Hydrates means when you hydrate, it's H2O. So stuff with basically an extra oxygen kind of thing, right? Because what is the difference between hydrocarbons and carbohydrates? You add oxygen, okay? So it is sugars, right? Sugar is like obviously when we say sugar now, it refers to table sugar, right? Which is sucrose, okay? But yeah, but obviously sugars is a very broad term in chemistry. It's very big. So, you know, as you've heard of people who have done biology, or even not biology, but deoxyribose, deoxyribonucleic acid, right? Also known as DNA, right? You got the ribose, which is ribose sugar. So that's a sugar there, right? So this is very important to know as a carbohydrate overall, okay? So monomer of carbohydrates are specifically called monosaccharides, right? And what are the three you need to know? Glucose, fructose, galactose. You need to know that these three are your monosaccharides. Definitely need to know this, okay? Glucose is the one that you have your structures on the chemistry formula sheet, okay? So that's very important to know, okay? Now, dimer, so dimer is your disaccharides, right? So your disaccharides are essentially a combination of monomers, okay? So sucrose is your first one, all right? Can someone in chat say what is sucrose made of? What two monomers are they made of? First person to say gets bragging rights. Yeah, good. Yeah, perfect. Okay, good job. Okay, glucose plus fructose. Okay, this is table sugar. Sucrose is table sugar, right? What we use. Okay, cool. Lactose. Who's next? Yeah. Okay, yeah, glucose and galactose. How do you remember this? Pretty straightforward. You have the word lact in there. Okay, just keep in mind all of these three disaccharides involve glucose because glucose is is involved in everything. But galactose is involved. You can know lact is for lactose. All right. The person who said milk, very good, because what's the enzyme? Lactase. Lactase is the one that breaks it down for people. Just because, yeah, galactose. Yeah, exactly. That's definitely relevant to this. Lactase. People who lack that enzyme lactase is people who are lactose intolerant, right? So that's just a fun fact for you guys. So anyway, maltose. Okay, chat. What's maltose? Yeah, beautiful. Glucose, right? I'm not sure if you guys heard of malt before, but malt is, yeah, like if you've ever had malt, it's pretty sugary. You could probably remember it that way, but to be fair, it's not too much to remember, okay? Those are your disaccharides. Very important to remember what they're made up of. It probably might, more or less, will come in a, a multiple choice question, right? But, I don't know, could come in a common week. Okay, starch. Amylose, amylopectin, which are like the two types of starch, and you've got cellulose. So these are your polysaccharides when you add a ton of glucose together. Remember, glucose is the goat here, so we're talking only about glucose, alright? So this is very important. Yes, good, there we go. So we'll just quickly talk about starch first. So amylose, amylopectin, alright? Those are the two main ones that I've written, and this is very, very, very high yield. I'm pretty sure it came in an exam sometime. Like one of the external exams. So very high yield to know the linkages as people are putting it in there, which is good. So what is amylose? Amylose, very important for us to know, it's unbranched. Okay? Unbranched. It's best to actually look these up. I probably should have put the images in here, but you'll be able to see them. But it's an unbranched, first of all, and it's alpha. So could anyone tell me what the alpha glycosidic linkage is? What does that mean? So for example, in cellulose, right, it's beta, right? So what does the alpha mean in there? Yes. Yeah, exactly. Yeah, perfect. So essentially the alpha means the oxygen, right? Which is in the bond that's like essentially below the plane of the sugar, right? So that's very important. Different general shapes. Yeah, I mean, okay. So with that question, would you be able to explain the different general shapes that amylose, right? Okay. First of all, I think best, like I'm probably gonna butcher it at the moment right now, but best is first to search up the like larger structures, like the actual image of it. But then in terms of what I'm covering right now is what you need to like know in terms of what to write in the explanation, if that makes sense. So as people have mentioned, it's carbons 1 and 4, right? But you also have amylopectin, right? I'll just quickly talk about this, which is a branched, right? Which is alpha 1,4 and alpha 1,6 as well, right? So this stuff is stuff that you need to know theoretically, but for the person who said to get the general shape, best is to look it up on Google, like images or something, and see the structure. Yeah, it'll make a much more sense than me drawing it out at the moment, definitely. Yeah, but you can imagine, like, okay, you know what? A piece of advice, right, for this stuff, draw them out. So, like, obviously look it up and then draw it, because obviously it's glucose molecules, right, combining with the alpha 1,4 and alpha 1,4 and 1,6. So if you draw it out, looking at the, you know, which one's branched, why is the other one unbranched, you'll notice everything, right? That's probably the best way, okay? No, this is not in the formula book, and that image there is really good. Yeah, that's a very generalized, like, yeah, actually, you know what, that's a really good, I love that whoever drew that art, it's very nice. So that's super good. Cellulose, is, oh yeah, Mars, oh sorry, yeah, there you go, that's very nice, yeah. So cellulose as you can see in the image, is basically, it's a crystalline kind of structure, right? So again, also glucose, polysaccharide, right? But glucose is now joined by the beta 1,4, okay? So that's the main thing. But obviously, you just need to memorize, like, cellulose. As you can see in the above one, it's a very, like, crystalline structure. There's bonds all over, and we know, like, generic salt, which is crystalline structure, is very strong, right? So cellulose, fun fact, because it's so strong, you actually can't, like, for example, we can't eat cellulose because it's very difficult to digest, because our body can't break down those bonds that are within them, essentially. So that's why, like, for example, corn, if you eat corn, you'll see it coming out the other end exactly as corn, because you cannot digest corn. But, for example, cows can, because cows have, like, full stomachs, whatever. Okay, I digress. But point is that it's insoluble, and it is indigestible for us, okay? So because of that kind of structure, yeah, cool. Does that make sense? Alright, hopefully it does. This is quite high yield. Alright, check the chat, okay, yeah, again, as everybody, hopefully there's people answering the questions as well, but I mean, yeah, Maz is also in the chat too, but yeah, hopefully I don't miss any questions there. Alright, lipids, again, high yield. So what are lipids? Monomer, okay, this is kind of the annoying part, because it kind of breaks down with lipids in terms of the monomer and polymer, but if you really want to put a name to it, monomer is fatty acid, like fatty acids are the monomers of lipids, and then triglycerides are the lipids itself, like the polymer, right? Like, yeah, again, kind of, right? So fatty acids, let's talk about fatty acids. Very straightforward. It's basically a carboxylic acid, right? You have the carboxylic acid and massive chain at the end. This is a very gross picture of, when I say gross, I mean like crude picture of a fatty acid, of a skeletal structure of a fatty acid, basically, right? So you have the carboxylic acid group with a massive hydrocarbon chain, right? And when I say massive, it can go for literally so long, right? Generally the ones that you see might go for, like, 30 or 40 carbons, but it can go way longer than that. Again, something to note, a little bit of a real life, like, kind of, I guess, relation as well, right? You've got unsaturated fatty acids, right? What does that mean? Unsaturated means that it has a double bond, right? So mono unsaturated means one double bond, right? And then poly unsaturated just means it has several of those double bonds, so like 1 plus basically. Okay, so yeah, these are essentially like the two main fatty acids that we have, like we need kind of thing. All right, and okay, we've kind of discussed intermolecular forces above, but if you increase the length of the carbon chain, what do you guys think will happen to the melting point? Yes, exactly, increase, right? What about if we decrease the level of unsaturated, or in other words, if you decrease the level, like number of double bonds? Yeah, it also increases. Perfect, exactly. So that's two ways. So increase carbon chain, right? And then decrease unsaturation, or decrease the number of double bonds, right? That hopefully makes sense. Okay. And then obviously you've got like cis and trans, so you've got that geometric isomerization as well, with the the unsaturated ones, because you've got a double bond as well, so just keep that in mind. Okay, triglycerides. So triglyceride is, yeah, kind of like a polymer, right? But essentially it's where I think this is also called triglycerol or triglycerol or something like that, but triglyceride just means 3 fatty acids and essentially glycerol group connected to it. Okay, so does that kind of make sense? Yeah, hopefully. Okay, so if I were to draw, I'll just draw a quick, I guess, example. But you got CH2, right? CH2, all right, and then you got your carboxylic acid group, very important, right? And you got your massive carbon chain. Okay, so this section is a essentially a triglyceride. You can see this. What is that? That is essentially your fatty acid, your 3 fatty acids, right? And this part is technically your glycerol group, which is formed from CH2, CH, CH2, OH, OH, OH. So, can somebody please tell me, this glycerol group, you add to this, what type of reaction is that? Yeah, bang. Condensation, esterification, exactly, right? Yes, okay, perfect. So that one is pretty straightforward, right? Because obviously you combine a alcohol, which is glycerol, it says it's in the name, and then you combine a carboxylic acid group with a massive carbon chain. It's essentially a esterification, right? We'll talk about it a little bit more about later, but essentially now we'll talk about saponification, right? Okay, this is a bit of an issue because I do not have enough space. But saponification, I love. Okay, the way you also know saponification is base hydrolysis, and I love this. Right? Why? Because it has the word hydrolysis in it. Okay, this is super important because if you have a triglyceride, right? What's the opposite of esterification? The reason why I asked you guys what type of reaction is the opposite of esterification or condensation is hydrolysis, right? So hydrolysis is done by a base. So saponification, another word for it, is base hydrolysis. I love that, right? That's really good. So essentially it's where you get triglycerides and like you put essentially aqueous, say for example sodium hydroxide, right? And then you break those linkages. So essentially, right, let me try and see if I can get the, oops, no, if I can get the rubber out of it. Holy crap, this is so annoying. Okay. Let's just rub this out. So the top part out here, right? Yeah, perfect. Okay. So we have CH2, CH2. So I'm just drawing a triglyceride out, by the way. Okay. So you add 3 NaOH, and you'll see why 3, because you add to the separate 3, I guess, like, fatty acids, right? And then that will essentially convert or go into the glycerol group, so break it up. Remember, it's breaking up into its reactants, so CH2, CH, OH, sorry, that's supposed to be there, CH2OH, right? And where will the Na, so the OH part of it, right? Well, yeah, technically, yeah, the OH part of it's connected there. and the Na parts essentially connect to everything else. So it creates 3 Na, and you got your O, C, oxygen, and you got your massive thing, because the Na combines to where the H plus used to be. Okay? Perfect. So saponification. Okay, so I guess this is a very important thing. I probably should have put another slide after this. Okay, you know what? I will check another slide real quickly. Because yeah, this is very annoying. Keep that. Add a slide. Alright, let's go from there. Alright, beautiful. Alright, so now we'll talk about a little bit about, we'll talk about base hydrolysis, right? So what does this create? So, this piece here, what is that? Guys in the chat, what is that? Oh, sorry, let me, what was that question? When approximately will this masterclass finish? Very good question. Whoa, okay. How far are we through? We're at 35 of 49 slides. My guess would probably be, hopefully, like 10, 15. Let's go for 10, 15. I'll try to finish between that. Yeah, so, good. Okay. So essentially the 3 Na, or we can technically remove the at 3, but Na, O, C, that, and the massive chain. This is a soap now, okay? Why? Because we have an Na connected to it. Okay? Correct me if I'm wrong, but from memory, this is called a sodium, like palmite or whatever. It's like a really weak name, palmite or whatever. Okay? So this is a piece of, yeah, palmite. Exactly, palmite. You know what? No, I honestly don't think you probably don't. You just need to know this is a soap, basically. Because palmite, like, that's probably not even IUPAC because it's not like, using, like, the parts of it. So, what did amphipathic? Oh, I'm literally about to talk about that. So that's very good you brought that up. So yeah, so very good question. Okay, amphipathic is a very important thing, very high yield, right? Essentially, amphipathic, right? What does that mean? You have essentially two polar stuff, right? Sorry, not two polar stuff. One polar, one non-polar. So essentially here, what is this? All right, we have oxygens. As soon as oxygen comes into the thing, it becomes a hydrophilic, or in other words, polar head. Okay, hydrophilic meaning loving water. Okay, what is a hydrocarbon? This massive chain with only dispersion forces, right? That is a non-polar or hydrophobic, or in other words, lipophilic. And we'll talk about lipophilic later on. Tail. Because it has a polar head and non-polar tail, it is essentially two contrasting things, right? If you guys have done English, what would that be called? It's probably called like an oxymoron or like a juxtaposition or whatever, right? You've got like two opposing things next to each other, right? That is called amphipathic, right? It's when it contains a hydrophilic head and a large hydrophobic tail, right? This is because of the carboxylic functional group. You have the polar, and then you have a carbon chain which is non-polar. Okay. Does this come down to the polar? Yes, definitely. And well, because this is two parts of it, I'll bring that in definitely. And yes, it does. So polar dissolves polar. So polar, like dissolves like, right? So we'll definitely talk about that, which is the micelle thing which the other person brought in beforehand. Okay. So this amphipathic nature of the actual soap is super important for actually how soap works, right? So what is dirt, what is grease, what are oil, right? These are oil droplets here, right? What is oil? It's like lipids, it's lipophilic, right? It's oily, it's greasy, okay? It doesn't like water, because we know that oil and water do not mix, okay? So how does soap act? What we see is this one is lipophilic. So what will the lipophilic? So let's just what is this? This will, let's just condense into this. So this is the hydrophilic head, and this is the lipophilic tail. Okay, let's just condense it to that. Okay, so the hydrophobic or lipophilic tail will insert itself into the lipid, right? And you have the hydrophilic head outside. Okay, so all of these like soap molecules will come and put their hydrophobic tails or lipophilic tails into the oil or the oil molecule, right? While the hydrophilic heads stay outside. with the water. So this is all water around it, right? So they stay on the outside. Okay. So what happens from here, right? The soap essentially keeps on breaking down the oil. Can anybody tell me why does it not stay like this? Why does it break down? So why does this oil not stay like this? Why does it keep on breaking down with more of those molecules thing? Yeah, this is the micelle. Yes, exactly. This is the micelle, right? This is the micelle. Why do you think it was? Why is it breaking down into smaller oil molecules? Why doesn't it just stay as one gigantic oil molecule? There's a very specific phrase that I'm looking for. Yeah, I mean it's polar, but why don't they just polar like? Not necessarily. Emulsification. Yeah, emulsification basically, right? What does emulsification mean essentially, right? It's relevant to surface area, super important. Okay, these lipophilic or hydrophobic tails they love oil so much that they want all of the molecules to come in, right? So they want the whole gang, the whole family to come in and just get this oil. So these guys, what happens when it breaks up into two smaller molecules? It breaks into two smaller molecules, but what happens? Increases the surface area of the oil. So when you increase the surface area of the oil, you can chuck more of these soap molecules and they can have more, right? So that is essentially why it breaks up. So continually breaks up the oil because it wants to increase the surface area. And after that, just to a point where the water just washes it all of that away. Okay, so just keep that in mind. The surface area point is important because I guess okay, this is actually good. What could possible questions be where you're applying? So they could literally just ask you, how does saponification work, and please explain the action of surfactants, right? Or like soap, right? And then high yield words would be like emulsification, would be increasing surface area. Obviously all is amphipathic, polar head, hydrophilic head. So yeah, real. QCAA will never say please, that's so real. Yeah, exactly. What was again that breaks down and surface area increase? Yeah, okay, cool. That's okay. So this is the oil droplet, right? Let's chuck some of these soap molecules in, right? So let's say there's 1, 2, 3, right? Okay. When you break this down, right? So it goes when the soap molecules break it down, right? Why do they break it down to two smaller ones? Because then more molecules, more soap molecules will be able to attach because there's more surface of oil to attach to. So more of the soap molecules will be able to attach to the oil. Okay? Yeah, okay, cool. So, yeah. Yeah, exactly, yeah. Cool. Alright, something also important to know about this, hard water, I brought, that's something important to bring in, okay? Hard water is especially important in Queensland, because, as you guys probably know, water kind of sucks here. Especially, like Victoria and stuff, they have really good water because it, passes through marshes. But anyway, I digress. There is a lot of, essentially a ton of metal ions in our water, okay? So what happens when we have a lot of metal ions in our water? So what, you know what, again, sorry guys, I will be making another slide. I should just chuck a ton of slides between each file. Oh, whoops. Alright, okay. Let me just add another slide. Okay, boom. Alright, okay. So, hard water, what happens? So, what are metal ions? So, we've got Mg2+, we've got iron, we've got magnesium ion, we've got calcium. Calcium's a big one. I'm sure you've seen calcium at the bottom of kettles and stuff like that, right? So, essentially, when you use soap, right, which is your Na, right, this molecule that we have here, so, yeah. Okay, what happens is these, essentially, when we use the soap, the metal ions, they essentially try and neutralize that charge on the hydrophilic end of the soap molecule. So essentially, they neutralize this, they combine with it, and then they create a precipitate, right? So when they make insoluble, so they precipitate this. Like, this is probably not the exact thing, this is probably not chemically correct, but you get the point. Like, they essentially attach it, they compete for it, and they create a precipitate, they create an insoluble compound. Point is that this is insoluble. So what happens is, if it's insoluble, it doesn't like dissolve in water. So essentially, it just goes out, makes soap action very ineffective. So what happens is that you just have to use more soap. Okay, that's basically it. Cool. Okay, let's keep on going because this is getting quite long. Okay, proteins, very high yield. Okay, so this is low-key probably one of the most high yield ones out of the organic molecules. I know I'm saying this a lot. Okay, I feel like I'm saying this for every topic, but proteins are high yield. Okay, so proteins, monomer. This one's a definite monomer. It's not a kind of monomer like lipids. It's amino acids. Okay, polymer is polypeptide. Can somebody tell me the difference between polypeptide and protein? This is a very niche thing, but if you don't know, that's all good. It's very, like, I don't think they'll ever ask you that. I just want to ask that. So, yeah, real. So, yeah, polypeptide is just the pure sequence of amino acid. Okay? Yeah, it's many amino acids, exactly. Right? But then, protein is the actual, like, polypeptide folding. Right? It like, like if you guys done bio, right, Golgi, like the endoplasmic reticulum, or the reticulum, the Golgi apparatus, they're all involved in the folding of these proteins, right? So essentially, when they fold the proteins, that's what becomes the actual. Sorry, when they fold the polypeptides, that becomes what the protein is. Does that make sense? Yeah, exactly. So we'll talk about the structures. They're definitely involved in those structures. We'll talk about them. That's the biggest high yield thing that we'll be talking about today. Yes, exactly. So polypeptide by itself, the sequence of amino acids doesn't mean anything. Like like amino acids build up polypeptides. Polypeptides cannot do anything. It's useless to our body. Once it starts folding is when it gives that polypeptide function, and when they give that function is what it's called a protein. Okay. Yes, we need to learn quaternary structures, but it's very general. You don't need to know much about it. Like, what I'll cover today is probably all you need to know about quaternary structure. Okay, cool. I'll quickly cover this. Okay, what's an amino acid? Alright, very important to know the structure. Super important, okay? It's an amine, okay? We have that, right? We have an amine group. You have a central carbon, right? That's a hydrogen. That's the R side group. And you have a carboxylic acid group. This is so important to know, okay? Amine group, carboxylic acid, side group, and the other random hydrogen just because carbon needs 4 bonds. Okay? Alright, something we'll quickly go to Zwitter ion really quickly, okay? What is a Zwitter ion? It's essentially where this H loves to leave, okay? It leaves the gang here, and it attaches to this side, the H3. So this becomes a negative-sided group, negative-sided functional group, and this becomes positive because you remove a H and you add a H to the other side, okay? So this is essentially where it becomes a negative on one side, positive on the side. What happens on a positive and negative? They cancel out, right? So overall, the molecule is a neutral charge. Overall, it's a neutral charge. However, right, they both have like poles in a way. They're like dipole kind of way, right? So essentially, neutral charge overall, but they have 2 poles of this plus and minus, and that is what's called a Zwitter ion. Okay. I literally could be making this up, but I'm pretty sure it's like German or something, but I could be making that up. Okay. So that's what a Zwitter ion is, and that's what an amino acid is. That's very important to know, alright? So you can see how amino acids combine next to each other, by the way, because, you've got the carboxylic acid and amine groups, like combining together, alright? Cool. Alright, and you should know based on the R side groups, the side chain, so this R, right? Oh, okay, yeah, this is actually very important. There's like 20 amino acids, right? The amino acids only differ because of this R side group. So there's about 20. Some of them are essential. I think like 11 of them are essential amino acids, so like where they're found, like, yeah, something like that. Anyway, but you need to know the R side groups and what makes them polar, what makes them non-polar, okay? You should be able to work them out from the structure, okay? Alright, now let's talk about each of the protein structures, and I will, again, take a bit of time to try and oh my lord, okay, this is super annoying to work with, to get another slide in. I really need to figure this out for the next masterclass. So I've got a year to figure it out. Okay, you know what? We're just gonna go with this. We're gonna go to the slide. It's not working. Okay. Okay. Primary structure. All you need to know: sequence of amino acids. That's it. Okay. When you have a ton of amino acids together, creates a polypeptide chain. That's it. Okay. Secondary structure, tertiary structure are the super high yield ones that you need to know. Okay. They'll, like, if you do get tested on this, they'll just literally just ask, compare the structure of proteins, and you just need to write a massive essay on all this. Okay. So, yeah, actually, really quickly about the linear, linear sequence of amino acids. Just to keep in mind, right? You've got your the amine group on this side, and you've got your COOH group on this side, right? Just keep in mind what happens, right, to form it. So you've got your COO, right, and then this combines to the N, right, and that's called a peptide bond. Okay, so that's a very important thing you need to know. So it creates peptide bonds, right? Okay, so difference between secondary structure. Secondary structure, very important. Hydrogen bonds between backbone atoms. Okay, not side chain. This is very important to know. It's not the side chains. It's not the R. Okay, we are talking about the backbone atoms, the hydrogen bonds between them. Okay, so essentially we have the alpha helix, beta pleated sheets. Okay, please look at a photo of it. Like you've probably seen it already, but it's very straightforward. It's like a helix like this, or it's like sheets like this. Okay, and that's essentially where the amine group, for example, right? You have an amine group, the H here, right? And then you've got like the oxygen of this one of the carboxylic acid, and then there's like hydrogen bonding between them. So I'll just draw it here again as well. But you have a carboxylic acid here, and then you've got the H of the amine, and then they form hydrophobic, hydrogen bonds between them. Okay, so this is the formation of hydrogen bonds between the backbone atoms, which means the backbone is this one, right there. Okay, that's like a lot, like that's like a very like overall kind of general kind of explanation of secondary structure, right? If you want to remember anything out of like proteins, like structure, just go hydrogen bonds between backbones. What is tertiary structure? Between side chains. Okay, the side chains are very important now. Okay, these are the stuff. Okay, this stuff right here where I've listed, please remember these, memorize them or whatever. Okay, they can form hydrogen bonds, ionic interactions, hydrophobic interactions, disulfide bridges. Disulfide bridge is probably the most high yield. They'll probably be looking for that. Okay, so very important to remember these four. Okay, memorize them. You should just be regurgitating them in a exam when they ask for that. Okay, so I'll quickly explain each of these. So hydrogen bonding, we've already talked about that, so we're not going to talk about that much. But it's essentially if there's any hydrogen bonding between the side groups, right? Ionic bond, it could literally be like a NH3 plus, right? And you've got like an O minus or something, and bang. Okay, that's an ionic bond, right? Surely we know ionic bonds. Okay. Hydrophobic interactions is essentially where you've got CH3, CH3 interactions, kind of like, back hydrophobic. They're like hydrophobic, they're just interacting. Honestly, do not ask any more questions apart from those hydrophobic. I don't know like too much about the hydrophobic effect, to be fair. Okay, disulfide bridge is super easy. Two sulfurs connecting, and this is basically, as I mentioned, between cysteine residues. So if you have two cysteine ones that like combines, creates a disulfide bridge, and hopefully we know the hydrogen bond. Okay. That is a very quick summary of this tertiary structure. Quaternary, this is all you need to know, but essentially it is combination of multiple polypeptides, right? So if you have like 50 amino acids, for example, of polypeptides, and they're essentially combined together, like combine multiple polypeptides, and that's essentially forming the quaternary structure. Okay? So yeah, hopefully that makes sense. Okay? Alright. Let's just check the chat really quickly. Oh, we've got one here. You need to know the covalent bond stuff. 2010 external marked you down if you didn't mention covalent bonds for tertiary. Yeah, exactly. Oh, covalent bonds for like the tertiary structure. Oh, disulfide. Okay, yeah, okay, there you go. That's I imagine that's really important. Yeah, exactly. Super important because it's two sulfur atoms combining, so that's so fair. Yeah. Cool. Makes sense. Alright. Yeah, sorry. I didn't invent the QCAA. Sorry, guys. I'm only a slave of the QCAA. Oh, yeah. Isoelectric point is super high yield. Please remember isoelectric point. I'll just a quick rundown of isoelectric point is essentially where the point at which it either turns an acid or it has acidic effects or alkalinic effects or basic effects. So because we know this is around here, so it's whichever, yeah, whatever, like which way it goes, whether it's an acidic environment or a basic environment, it will interact in different ways. What interactions do we need to talk about in quaternary? Just the polypeptide. So two or more polypeptide chains combining. That's literally all you need to write down. Probably like just combine. Okay, polypeptides. Several polypeptides, two or more interactions between these polypeptides creates a quaternary structure. Okay. And generally, like if you want to go like really far ahead, you can talk about like the actual like examples if you want, like hemoglobin and stuff like that. But yeah. All right. I know enzymes are not here, but I saw a bit in the chat. But yeah, enzymes are proteins. Yeah, just keep that in mind. They essentially like make it faster. Any reaction. Lock and key. Now you don't need lock. Lock and key is essentially like where the substrate. So you've got like substrate. So this is the active side, and then you've got like the enzyme, which is perfect for the. It's like the key is the enzyme and the substrate is the actual like active side, and that's the shape exactly matches. So it's like a key going perfectly into a lock. That's essentially it. Can you explain what denaturing proteins and enzymes are and how they become denatured? Okay, you don't need to know too much about that, but essentially, denaturing of proteins enzyme generally happens to like heat, or any any UV kind of thing. Like it's essentially where it destroys the proteins and enzymes. And so that's basically like denaturing just means it's breaking down, and how do they do that is what I mentioned, heat and UV and stuff. For example, like a lot of that's why our body temperature is so tightly regulated at 37 degrees, is because our proteins and enzymes within our body needs to work at such otherwise they get denatured, right? If it gets too cold, they like slow down, or if it gets too high, then they get denatured and stop working. Oh, yeah. Sorry. Wait. Yeah, exactly. Lock is the active site and the substrate is the key. Yeah, well, sorry. Yeah. I'll just explain that way too quickly. Alright, cool. But yeah, enzymes are high yield. You probably just need to know for bio, probably. Okay, what's next? Yeah, question. Perfect. So this is a very straightforward question. This is also in the 2021 exam. So if you want, you can take a screenshot of that and work it out. But essentially, it's like you essentially just need to look and which one is which enzyme. Sorry, which one is which amino acid. Okay. So yeah, cool. I'll go next one. Analytical technique. So this is this is probably mid-yield. I would say they will probably bring this up, like an IR spectra or like a mass spec or even a chromatography, which I was in my 2021 one. So you could bring up anything, to be fair, right? So chromatography, protein analysis, right? Based on physical chemical properties, so like size, charge, hydrophobicity, right? It's very important. So there's different types. The one I think you may need to do is the size exclusion one. It's really easy. It separates by size. Literally like a sieve, right? You put it down the sieve and just based on size kind of thing, it just, differentiates that, right? There are other ones like ion exchange chromatography and affinity chromatography, which you probably didn't need to know. But ion exchange is where you separate by the charge. Okay. Electrophoresis, so I'm just going to speed going through these for proteins. You need to know the SDS page and the native page. That's very important. So SDS page is that massive name that, please don't ask me to say. Separates proteins by the molecular weight. Okay? So something that's very important is that the SDS gives the proteins a uniform negative charge, and a native page maintains the protein's native structure, hence why it's called native, right? And that's just basically based on charge and shape as well. Okay? Cool. Let's keep going. Mass spec. All you need to know about these two, mass spec and X-ray crystallography, is how they work. Well, and I guess mass spec, you need to know how to read it as well, the MZ ratio, so mass to charge ratio there. But X-ray crystallography, these are the steps. You crystallize the protein, right? Fire X-rays through it and analyze the diffraction pattern. What happens is essentially when you fire X-rays through it, you'll get essentially dots where the actual atoms are, where it's essentially rebounded. and then like and you get like the everything else is where like the X-ray's gone through, so it creates like kind of like an X-ray image, right, of the actual like atom or like whatever molecule you're looking at. So, and then you analyze that. In terms of mass spec, you vaporize like it's something like you vaporize the sample, and then you essentially send it through a magnetic field. If you want to know about magnetic fields, look at my physics one. No, I'm joking, don't bother. But yeah, you send it through a magnetic, you accelerate it, deflect ions in the magnetic fields. I think you just like shoot electrons at it at one point as well. And then essentially fragments it at the end. So you have like a lot of fragments of the actual total molecule. And essentially what happens is it goes through a detector and it detects the different fragments and then essentially graphs all of those fragments based on their mass and their charge. Okay? So that's essentially, I guess, yeah, that's how the mass spec works. You don't really need to know how mass spec works, but like mainly you know like what it looks like. So you'll get like an image like that, and then it'll have like, you know, like this, where they tell you like, you know, the mass and spec, mass and charge ratio. IR, yeah, this is probably really important. There was a question last time in the physics masterclass that I went through with someone about IR. Is just look at, this is really, like, it's, I actually don't think I brought a question for this, unfortunately, sorry guys, but, you know, you have your transmitters, right? That is a beautiful IR right there, okay? This essentially, just look at every big peak. Okay, the biggest peak, so generally like ones that have like, you know, 70, maybe 70% above transmittance and stuff like that. And look at all of the, like maybe even write it down. And look at all the wavelength numbers and write all of them down, right? And then essentially identify from there what functional groups you have, okay? I can guarantee you, like the person that did it last time, that showed me a question last time, right? All you have to do is just know, like, associate all the big peaks with the numbers, all of them, like most of them, right? And then you essentially like from there kind of look at the commonality, right? So if it's like a aldehyde group, right? There's aldehyde, like a carbonyl group. There's also a carbonyl group and a carboxylic acid as well, right? So just keep that in mind. Just remember the functional groups that are involved. Okay. Yeah. Does that kind of make sense? Hopefully. Okay. Okay, can you please show the native page stuff or something? Oh, okay. Genuinely, for the native page stuff, you don't need to know much. Okay? All you need to know is, okay, maybe just know like, yeah, this point, right? So essentially, the protein, it maintains its normal shape. Okay? That's basically the main thing you need to know about native page. Okay? And like SDS page probably like not even that important, but like yeah, like there's not much you need to know about electrophoresis. Okay, the only thing you need to know is how electrophoresis, like what's the outcome of it, which is basically just separates proteins based on their like charge. Technically size, because size affects charge as well and the shape of it. So yeah, not yeah, don't stress too much about it. And then how do we do the X-ray crystallography to analyze this stuff? You won't need to analyze like yeah, as far as I remember from the syllabus point, you won't need to analyze the X-ray crystallography itself. Like it's just like you'll be able to see it and it'll work it out because it's like X-ray going through the actual crystal structure. But as far as I know, you just need to know how it works. But I could be wrong, so please someone let me know if that is different. If I'm wrong there. Oh, real. Okay, IR spectral tips. Okay, yeah, I think literally like what I mentioned before, the best thing to do, okay, so just identify all large peaks. All, okay? Just go through all the large peaks, right? I can guarantee you, so if you have another tip with it, after you've done that, right, you'll get like carbonyl, like they might, like on the actual chemistry formula sheet, it'll probably be like aldehyde, ketone, whatever, right? And you'll have another, this will be a number, let's just say 1035, okay, that could be a random number, but then you have like 3050, which is like carboxylic acid, alcohol, right? So when you've identified all of them, these can have overlaps between them, right? So if this one is 3050 and this one is 1035, you might think it's an aldehyde, but it might actually be a carboxylic acid, because carboxylic acid also has a carbonyl group which is also present in the aldehyde in ketone, right? The following is the electron density. Oh, yeah, no, I hope to God, no, holy, yeah, no, that's not, yeah. If that is genuinely, like, yeah, please complain. Yeah, hopefully that you don't need to know that. Cool. Oh, select new data. Okay, let's say that. Okay. To be fair, X-ray crystallography is not like if you look, okay, let me pull up a picture of what it might look like. Actually, let me just open up the textbook. Surely there's a picture. No, that's too much work. Let me just go through X-ray crystallography. Okay, maybe not. Okay, there's not any good images. I guess everything is pretty complex. This is the reason why I guess they don't put in, like, you don't need to infer, like, you don't need to, like, interpret any data for, like, when they say select and use data for that one, they mainly mean mass spec and infrared spectroscopy there. X-ray crystallography, they'll probably give you just this, right? They'll give you a circle, right? They'll give you, like, three things like that. Sorry, not three things. They'll give you a diffraction pattern where all of this is, like, colored out or like, you know, white or something. And then they'll be like, you know, oh, like, explain this diffraction pattern. And you'll just be like, this just gives, like, you know, the positions of the atoms in the compound. Like, it'll be very intuitive. Like, they won't give it, first of all, by itself. They'll probably give it with an IR spectra and, like, a mass spec. Yeah. Cool. Does that make sense? Oh, yeah, exactly. Yeah, that was the question that I talked about in the physics masterclass. So if you are just that desperate to go into that question, please look at the end of that masterclass recording for the physics for that question. But yeah, essentially what I did was I looked at all of those peaks there and then looked at essentially the similarity, like what are the, like, names that were the similarity between all of them. Okay, cool. Yeah, so I just saw somebody mention this as well. Yeah, it's about to end, don't worry. Yeah, I, like, basically skipped all of, like, the chemical synthesis, the heavy process, contact process, biofuels. Those are, just keep in mind, those are all applications of what we learned today. Okay? So we learned about, you know, what do you call it? We learned about, like, esterification, right? In terms of, like, the actual, like, saponification, like, not saponification, but in terms of creating soap, right? We know about ethanol. Technically, we should know about ethanol, right? We have the multiple methods of ethanol, so ethanol fermentation, the hydration of ethene, which we've already covered, right? So all of the chemical synthesis, just go over that, but it was basically all the stuff that we've covered. This is the application of the theory, right? We know about the Haber process, contact process. We should know that in depth. Super important to know that in depth. Especially equilibrium, Le Chat's principle in terms of that, right? I'm not sure if Ashan talked about the Haber process in terms of Le Chat's principle and equilibrium, but that is probably a question that could come up. Okay. So, and the contact process, I got a question before, like, do you need to remember all the form, like, the actual equations, the reaction equations of all of the contact process? I'll be honest, I didn't. I personally did not memorize all of that. I don't think you do, but please do not quote me on that, because it doesn't really say in the syllabus. Is it worth memorizing every reaction pathway? Okay, I did not go ahead and memorize every pathway. However, and this is a big however, I probably ended up, like, memorizing each reaction pathway because I did a ton of questions. The more questions you do, the more hard, like, organic chem questions you do, the more you'll realize, like, the more, like, reaction pathways you get into your head. Okay? So that's, yeah, but I definitely did not actively go out and memorize it. There is that Anki deck as well, by the way, like, that I created. I don't know if I totally forgot if there's reaction pathways on there, but that's the stuff that I needed to, like, make myself memorize. Where'd you get so many reaction pathway questions? Interstate, 100%, and that's one of my like feedback / advice at the end. interstate questions, please look up. I mean, I don't know if you have enough time now, but waste papers are probably closest to QCAA in terms of like difficulty level. But VC, HSC, those have pretty hard questions as well. Because unfortunately, organic chem is where theoretically they could bring the harder questions in. Like if you guys have done an organic uni level course, which I did, it is well and truly cooked. Like you guys, like I had no idea what's going on half the time, right? They start off really easy, like with this stuff. Oh, sorry, I didn't call this easy, but they start off with this stuff, right, which is pretty good if you're kind of in year 12, and then they just exponentially increase on how it is. So, how do you have time to do interstate papers? Yeah, good question. Yeah, this timetable really important scheduling. Okay, let's cover this question, guys. Okay, because I do want to finish this off really quickly. Okay, so yeah, question. Different reaction starting with compound A, which is an empirical formula, and for a class of organic compounds. That okay, what do we think? What's compound A, guys? What do you guys think? Yes. Okay, thank you. Alcohol. Why alcohol? We have multiple things happening here. We've got a carboxylic acid which creates an ester. We have chromate here, which goes to a carboxylic acid. We have a double chromate, so we've got two oxidizing happening, right? And then, wait, what? Can you guys not hear me? Hello? Wait, yeah. What? Can you guys not? Yeah, okay, that's really weird. So some people can hear, some people can't hear. What just happened? I don't think anything happened, guys. Nothing has changed on my end. Hopefully it's something to do with your end. I will charge my iPad there because it's low on battery, but nothing happened there. No, my mic is, okay, hold on. Mic is not muted on iPad, which is where I am talking through. Yeah, hopefully, yeah, cool, okay. Okay, yeah, so I'm assuming people can still hear me. Okay, I shall continue. Okay, so for the people who can hear me though, we've got compound C, so compound C, which is this one right there. Oh yeah, I didn't talk about this as well. So we've got alkene, which forms C and A, which we'll talk about. So compound C is an isomer of compound A. So compound C, isomer of compound A. Deduce the structural formulas and the IUPAC names for compounds A and C. What do you think that compound A is? Oh damn, okay, that's good, awesome. Okay. Yeah, I genuinely, I did not do anything different, guys. Like, I just kept on going. So, yeah, anyway. Compound A. What do we think compound A is? Yeah, good. Exactly. So, compound, yeah. So, yeah, okay, cool. Okay, so compound A is butanol. Okay. So, I'll show you guys how we work that out, but holy crap, sorry, there's so many issues right now. That's really annoying. I will try and figure this out in the future. Alright. Hopefully the recording, you guys can still, yeah, thank you Sam for putting that in. Alright, cool. Okay, yeah. So butanol, right? So butanol is the RU pack name, and that's the actual the structural formula there. Why do we know? We know this is an alkene, and you add H2O to it, right? So it's a hydration, right? What happens when you do a hydration to an double bond? It creates a alcohol. Okay. And then what's the next one? Oh yeah, ibuprofen. So you just chuck a butanol there, right? I think next question is compound C. So technically we have two ways of adding this, right? So the next one is CC, and then you got OH on here, right? It's the same thing basically. So that's just the two structural isomers, right? So it's just the difference of like where the OH is. Okay, so that's the only thing. So this would be called 2-butanol, right? And the reason that's why it creates two different ones through a hydration reaction. Okay, so we've talked about this before. To identify whether compounds A I C are structural or geometric. Keep in mind these are structural. What are geometric? That's your cis trans, right? Cis trans. So this is structural isomers because the number of atoms have stayed the same, and they're just different where they are, kind of thing, right? Yeah. You're right. Technically, it's butene 2-ol. That's so true. Yeah, because you identified that the ol is 2. That's a very good point. But yeah, like they won't mark you down for doing 2-butanol as well. But yeah, cool. And then finally, I deduce structure formula and for compound F. So compound F is here, so it's your ester. So you've got compound A, which we here, and then combining with, what is this one, guys? What is this molecule? What is this? This is a carboxylic acid, but specifically what carboxylic acid do we have there? No. So yeah, ethanoic. So ester is this one, but the carboxylic acid, yes. Okay, we've got it. It's ethanoic acid. Okay, ethanoic acid, also known as acetic acid, which is also known as the main part of vinegar, right? So ethanoic acid. So we have ethanoic acid, which is this, plus butanol, which is this. Okay, and then this essentially water goes out, H2O, and that combines here to become a cool. Okay. Whoa, that was way too many. Okay. Can somebody tell me what the IUPAC name for the ester is? Yes, good. Butyl ethanoate. Okay. This is very important to know. Why is it butyl ethanoate and not ethyl butanoate? Yeah, what that person wrote. Butyl ethanoate. Why is it not ethyl butanoate? Yeah, exactly. Because it's the ethanoic acid. Okay, remember, ethanoic acid takes precedence. Well, I mean, this is a little bit of a difference, but because it's an actual reaction that's forming, but rule still applies because it's the ethanoic acid. This is the carboxylic acid, and that is the important one. All right, so that forms technically part of the suffix there. All right, cool. We'll go through another one really quickly. We'll just speed through these. We've got a structural isomer of them. Explain why the isomer is a saturated compound. Hopefully this makes sense because it contains only single bonds. Okay, this is obviously you need to write way more. I mean, this is only one mark, so low-key this could like be enough. But again, if I was me, I mean I am me, but if I was you, I would write a ton more because I'm just paranoid. But yeah, identify whether the isomer is primary or secondary. What do you guys think? Let's go. Primary or secondary haloalkane. So I just gave the answer of what it is, but yeah. Oh no, it is, yeah. Primary, secondary haloalkane. Oh, sorry. Yeah, just guess. What do you guys think? Primary or secondary? That's 50-50 chance. Yeah, good, it's primary. Okay. Primary haloalkane. Because it's right here. Okay, it's on the end. It has to be primary. Okay. Determine the structure formula of another isomer of that, right? The haloalkane. That is tertiary haloalkane. Apply IUPAC rules. So this one's pretty good, right? A tertiary can basically only happen when you've got it around in a circle, basically, right? So like that. So you've got a central carbon there, and you've got attached to that, attached to this, and you've got Cl there. So this is combined to 3 other carbons there, right? So this is a tertiary because of that, and that's basically almost like one of the main ways that you can only get a tertiary. So Can you guys name what this is? What's the IUPAC name for this? Quickly. I know it's a little bit like annoying. It's quite a long one, but what do you guys think? Thank you for copying those questions in. Ooh, no, a little bit off. A little bit off. Oh, okay. Rip. So sorry. Okay, I don't know genuinely what is going on. Yeah, maybe recording might be the best. Is it changing now? Is it like, yeah, is that working or not? Not really. Okay, hold up. You know what? I'll just unshare, reshare screen. Alright, let's just do that. Okay, that should work. Surely that works. Stop sharing. Alright. Okay, hopefully you just don't see anything right now. Alright. I'm gonna share screen again. Okay. It should be loading now. Okay. Thank you. Alright, awesome. Alright, I probably should have done that a while ago. Alright. So yeah, this is tertiary. What's the IUPAC name for that? Yeah, not exactly. Yeah, that's the one. Yeah, exactly. So 2-chloro, 2-methyl propane. Okay. So how we work this out? We got so all of this is on the second because this is your carbon chain technically. That can be a carbon chain. The chlorine group is on the second one, and the methyl group is on the second one as well. So 2-chloro, 2-methyl, and then propane is the whole carbon chain, which is propyl, right? So 2-methyl, 2-chloro, 2-methyl propane. Yeah. Okay. And then yeah, cool. Alright. Yeah, let's probably do that as a last question. Bioethanol, I know we didn't really cover this. Bioethanol can be rich in starch, amylose, amylopectin, starch. Oh no, we kind of did do amylose and amylopectin. So this is starch, you've got enzymes, turns to glucose, used turns into bioethanol. So this is a combination of multiple things. So this is what we covered today. We do not cover bioethanol too much, right? But explain the role of enzymes in converting amylose and amylopectin. So this one is like more or less you just need to know, but like what do enzymes do? Increase the reaction rate by lowering the activation energy, but you just need to say they convert basically this starch, right, to glucose, right, by essentially increasing reaction rate or like even making the reaction rate proceed, right, like by what specific reaction? Hydrolysis. Okay, you're essentially increasing the hydrolysis, and what does that do? It breaks the glycosidic bonds. Okay, cool. And then in terms of the next one, so describe the structure of amylose and amylopectin. We've covered this already, but monomer, right? Alpha glucose, right? Glycosidic linkages we've already covered. 1,4. This is 1,4 and 1,6, right? Chain structure. This is mainly linear, so not really branched, or you can write unbranched, right? This is branched, right? And then shape, I guess, like I think some people brought this in, but this is spherical and this is helix, right? That's just something you just kind of need to know. All right. Does that kind of make sense? Wait, hold on. Yeah, shape wise. Yeah, okay. Yeah, you probably do. Yeah, you definitely know, like, yeah, all of that. Including cellulose, as we mentioned before. ET and end time. This is the last question. Literally, there you go. See, we got, like, advice, so which I've kind of gone through already. Fermentation. Just bring in the reaction. Okay. C6, H12 or 6, which is what? Okay, yeah, this is glucose. And it converts to ethanol, or like bioethanol, whatever. And then you got CO2 coming out because it's obviously yeast and stuff, so yeah. And then atom economy, hopefully you guys know the atom economy. It's very simple, it's just a percentage. Right, okay, cool, that's basically it. Yeah, you guys know that. For the boiling point, melting point, IMF, intermolecular forces, that is, something you guys should make a, I guess, question for, like an ideal answer question. So yeah, definitely do that. General advice wise, I think you've covered in the physics one, but timetabling, Anki, study app, obviously AI is very, very, important. Cool. That is about what we have today. Sorry it went for so long. But, yeah. All good, guys. Thank you for attending. Sorry, I've got the technical issues are actually crazy. Alright, thanks, guys. Within state papers, how much should we be taking in terms of techniques and answer structure from them? Yeah, to be fair, just make sure you take mainly the theory from it. So, yeah, that's really important. So, if you, the main thing is the theory and the questions, right? That's basically the main thing. Mainly just doing a ton of questions is what, the interstate papers give you. That's mainly, yeah, if that makes sense. But, most of the questions that you do interstate, they will be sometimes, harder, than the actual, what do you call it, the harder than the questions in QCAA. Sometimes, it depends. VC and HSC generally are, sorry. Yeah, make sure, yeah, you do them liberally, because, or conservatively, sorry, because, if you do, all the random questions, there's a lot of stuff that you don't need to know as well. So that's important. Sorry, there's another question there. Do you include coefficients in molar mass for anatomy, atom economy? You told me to, but yeah, I'm pretty sure, yeah, from memory you do, yeah. So, yeah. You got any tips for predicting marking guides based on cognitive verbs for long mark questions? Oh yeah, it'll, similar to physics and stuff, it'll definitely be explain melting point, how the melting point is increasing carboxylic acid or something like that. So the just the thing, make sure the only really cognitive verbs wise, explain obviously means explain, but everything else, contrast and compare is very important. So compare means both negatives and positive, and the contrast just means, compares both similarities and differences, but contrast is just differences. That's something. Do you do private tutoring? I do, but I'll be stopping this year, unfortunately. Boo. Cool, guys. That's all good, guys. Thanks for coming in. Yeah, I swear I'll figure out the technical issues next time. Yeah, literally. Yeah, spam past papers. Yeah, I don't think you guys should be learning too much theory at this point. Yeah, definitely spam as many past papers as you can. I know you guys have other subjects as well, but just make sure you compile all the past papers and make sure you schedule them in your timetable appropriately.